Welcome to the Deep Dive, where we take your sources and dig into the most compelling ideas. Today, we're plunging into a really fascinating area where AI meets neuroscience. We're looking at this huge challenge, trying to connect what an AI model does with what's actually happening inside our brains.
That's right. We've got some source material here, basically a record from an AI consultation. Think of it as experts really grappling with this problem. They were focused on, how do you align the outputs, the predictions of these artificial neural networks with real brain activity, the kind of signals you'd get from, say, an MRI scan.
And this isn't just theoretical head scratching, is it? It's about the real practical difficulties, the nuts and bolts of trying to map AI onto the brain.
Exactly. It's super practical and
Mm.
potentially really important, both for maybe building AI that thinks a bit more like us, and also for using AI as a tool to understand our own minds better.
Okay, so let's dive into this consultation record. What's the absolute core problem they keep coming back to? The fundamental challenge here.
Well, right at the top, the main thing is this core alignment issue. How do you actually map what an artificial neural network, an ANN, is doing internally or predicting externally onto those real neural responses from the brain, like the signals from an MRI?
And the source material raises a pretty big question here, doesn't it? Like, can the parts of an AI, these nodes, even directly correspond to specific bits of the brain?
Yeah, that's a huge point they make. It really questions whether there's a clear, defined relationship. You can't easily say this specific node in my AI model represents this specific area in the parietal lobe or something like that.
Uh-huh.
That lack of a clear biological equivalent, that one-to-one mapping, it's just not there currently. And that's a fundamental sticking point.
So we're not building like a simple translation dictionary between AI components and brain regions. The basic structures just seem different.
They really do seem different. And this whole problem gets even trickier when you try to move between different kinds of data, different modalities, as they call it.
You mean like taking an AI that's good with pictures and trying to make it understand sound?
Precisely that.
Yeah.
The consultation looked hard at this. They talked about convolutional neural networks, CNNs, which are fantastic for visual stuff, finding patterns in images.
Right.
And they asked, can we just borrow that successful architecture and apply it to something totally different, like understanding speech or maybe cleaning up noisy speech signals?
CNNs are built to see edges, textures, shapes, applying that to voice, language, meaning,
hmm
and then trying to map that onto how the brain processes sound. That feels like a massive jump.
It's a huge leap. And the source really pinpoints why it's so difficult. Different kinds of data just have fundamentally different structures and features. With speech, it's not just about analyzing frequencies like pixels in an image. You've got multiple layers, right?
Mm.
There's the sound wave itself, but then there's language, understanding, meaning, even perceived quality. It's incredibly complex.
So the sheer multidimensional nature of speech makes it really hard to just take a vision-based AI and expect it to neatly align with brain activity for sound.
Absolutely. And these problems, the lack of direct mapping, the difficulty crossing modalities, they feed right into another major issue discussed. How do you even check your work? How do you validate your map?
Validation. You need some kind of benchmark, right? A ground truth to compare against.
Exactly. And a big chunk of the discussion was about that. How do you compare what the model predicts? Maybe it's predicting a score for speech clarity, like a TSAI score or some other quality metric. How do you compare that prediction with the actual neural data from someone's brain listening to that same sound?
Okay, so the model hears some audio, predicts a score, and you want to see if the brain activity matches that score or maybe matches the AI's internal processing during that prediction.
That's the idea, yeah. But here's the rub, according to the source. Without enough real MRI data or similar neural recordings serving as that ground truth, it's incredibly difficult to verify if the model's mapping is actually correct or just, noise. You just don't have enough examples of real brain activity correlated with the model's outputs to properly train or test whether your mapping idea holds water.
Sounds like a classic data problem, a bottleneck, but made worse because brain data is so complex and hard to get in the first place.
Precisely. And this gets us into the really interesting theoretical side of things, and maybe a slightly controversial idea they raised. Given all these problems, how are people even trying to make these maps?
What methods were they kicking around in the consultation?
Well, they mentioned a few technical ideas, like maybe using structures inspired by Jan's generative adversarial networks.
Okay, GANs, those are the ones where two networks compete, right? A generator and a discriminator.
Sort of, yeah. The idea might be to use that kind of push-pull dynamic to encourage the AI's output, or maybe its internal patterns, to look more like the characteristics of the real brain signals you're aiming for, trying to mimic the brain data's properties.
So make the AI generate patterns that have similar statistics or correlate strongly with the brain data.
Something like that. Yeah. But this leads directly to that really challenging question the source puts out there. Could it be that what we're doing right now, trying to find these direct links between AI nodes and brain activity, is just, well, backfitting?
Backfitting, meaning we find a pattern in the data first, maybe just by chance, and then we build a story or a model to fit that pattern without really knowing the underlying reason.
That's the core concern. The source suggests that because we don't have a strong biological theory telling us why a specific AI part should map to a specific brain part, or why a CNN should process sound like our auditory system, the correlations we find might just be things we notice after we run the experiments. We then build a model that fits those observed correlations, but it might not capture any deep, fundamental computational truth about either the AI or the brain.
So we see the AI doing X and the brain doing Y at the same time, and we draw a line. We don't necessarily know if that line represents a real shared mechanism. It's correlation, not necessarily causation or shared computation.
Exactly. It's finding patterns versus truly understanding the principles. That's the crucial distinction they seem to be highlighting.
Okay, that's a pretty sobering thought about the state of play. But the consultation didn't just point out problems, did it? They offered some practical ways forward.
No, definitely not. They had some very concrete suggestions, which I think is really useful.
Right, let's hear them. What are the practical steps researchers can take?
Okay, first suggestion. Be pragmatic. Start by trying out models that have already proven successful in related areas.
Like those CNNs we mentioned, even with the caveats.
Exactly. Don't necessarily reinvent the wheel immediately. Take an existing successful architecture, like a CNN, and just test it. See if you can get any reasonable alignment between its predictions and the brain signals for your specific task, maybe speech understanding. If it works okay-ish, great, you've got a starting point to tweak and fine-tune. If it just completely fails to map in any meaningful way, well, the advice is you probably need to step back and rethink the whole model or the mapping strategy itself. Don't try to force it if the basic architecture isn't suited.
Makes sense. Start with what's known to work somewhere, see if it translates at all. What else?
Second, when you do start experimenting, focus your initial efforts. Concentrate on the parts of the problem or the specific tasks where the effect you're looking for, the enhancement rate or the mapping correlation, seems strongest or most obvious.
Go for the low-hanging fruit first, where the signal seems clearest.
Pretty much. It's about being efficient with your resources. Don't spend ages trying to map something really subtle or noisy if there's a stronger, clearer potential connection you can investigate first. And if you try focusing on one area and it just doesn't pan out, doesn't give you the results you expected, then you make a call. Either abandon that specific approach for that area, or maybe go back to the drawing board and redesign how you're trying to tackle it.
Okay, prioritize the promising avenues. Good practical advice. What's number 3?
Third piece of advice links right back to that backfitting worry we talked about. It's about being really careful when you interpret your results.
Because we're still not sure about that direct node-to-brain region link.
Precisely. Since we can't be certain about that direct correspondence, the source warns against overinterpreting any mapping you find. Don't jump to conclusions and say, aha, this proves the AI processes information just like this part of the brain.
So treat the correlation you find as a clue, maybe a useful reference point, but not the definitive answer.
Exactly that. View the AI brain mapping results as one piece of evidence. The suggestion is to combine it with other data points, like how well did human listeners actually perform on the task? What did objective speech quality metrics say? Get a fuller picture. Don't rely only on the brain scan correlation.
Right. Triangulate your findings. Combine the AI brain link with real-world performance or behavior.
Yes. Fourth, they suggest a kind of iterative, step-by-step approach to validation and adjustment. Start simple. Maybe don't try to map the entire complex data of the AI onto the entire brain response at once. Just try predicting one single, relatively clear metric like that STOI score for speech clarity based on the brain data, or vice versa.
Build up complexity gradually. Test the basic mapping capability first.
Correct. See if your model can even handle a simple alignment task successfully before you try something much more ambitious and multidimensional. And if it can't succeed even on the simple task, that's a strong signal that you need to fundamentally re-examine your whole experimental setup.
And what would that re-examination involve? What options do you have then?
Could be several things. Maybe you need to simplify the data you're working with, perhaps use dimension reduction techniques, or maybe you need to try a completely different way of aligning the data, a different mapping strategy altogether. Or, and this is often key, you might need to figure out how to get more or better ground truth data, more relevant MRI or neural recordings to actually train and test your mapping more effectively.
That data bottleneck again. More relevant brain data is often the dream, but hard to achieve.
It really is. And then finally, the last sort of overarching piece of advice was keep an open mind, borrow ideas, and just experiment. Don't be afraid to look at what's worked in other fields. If someone found a clever way to align, say, a language model's outputs with user behavior patterns, could you adapt that technique for aligning a speech model with brain signals?
See if mapping techniques from vision or text processing could be repurposed for this brain alignment challenge.
Exactly. Maintain that flexible experimental spirit. Except that some experiments won't give you clean answers, they might just serve as references, pointing out what doesn't work or hinting at a new direction. It's all about continuous adjustment, learning from the data you get, and optimizing your approach as you go. It sounds like a very iterative trial-error kind of process right now.
Okay, so let's try and pull this all together. What's the big picture message from this deep dive into how researchers are thinking about AI brain alignment?
I think the main takeaway is that trying to forge this direct link between the computations in AI and the biological processes in the brain, well, it's incredibly ambitious and frankly really, really hard.
Yeah, the challenges seem pretty fundamental. You've got the lack of a clear one-to-one mapping between AI parts and brain parts. You've got the difficulty of making models work across different senses, like sight and sound, and relating that to the brain. And then this huge problem of validating any map you create without enough solid brain data.
Those are definitely the major hurdles. But the practical suggestions do offer a path forward, even if it's a challenging one. You know, start simple. Focus your efforts where there's the most promise. Be cautious with your interpretations. Build up complexity step by step, and learn from other areas. Keep experimenting.
So it sounds like building truly brain-aligned AI, or even just using AI effectively to understand the brain, it's maybe less about finding some perfect, pre-existing Rosetta Stone that translates between the two, and more about finding clever, practical ways to correlate them, to validate those correlations carefully, and to iteratively improve our models based on the limited data we can gather.
Yeah, I think that's a good way to put it. It's like building bridges based on observed similarities and pragmatic tests,
Yeah.
rather than assuming we already understand the deep structural or computational parallels, because maybe we just don't yet.
Which brings us right back to that backfitting idea. And here's maybe a final thought for you, the listener, to chew on. If our best current attempts at mapping AI to the brain might largely be finding correlations after the fact, identifying patterns that the data happens to show, rather than confirming a deep theory, what does that really imply about how we understand intelligence itself, both artificial and biological?
Right. Are we just getting better at describing surface-level similarities, building models that are good mimics? Or is it possible that through this iterative process of correlating and refining, we're actually, maybe indirectly, starting to capture something more fundamental about how computation works, whether it's in silicon chips or biological neurons?
A big question. Definitely something to mull over until our next deep dive.